which segues into my next point, which is the where of motion control. The where is you're going to move something from A to B. Now, to do this, normally you have an electric motor, something that's been around for decades, and I don't even know when the first one was built, somewhere in the past century, I'm sure. And for 50 years now, we've learned that we can control these motors in a little better way, so that instead of just turning on a light switch, the motor ramps up to high speed and then shutting it off. We've become a little bit smarter and use mathematics and ways to control the current that goes to the motor very precisely. So I can do a little example of this. I didn't want to haul a whole motor and electrical device into this room for a 5-minute speech, but I can sort of simulate this with just a basic tape measure. What I have here is a rotary spring-loaded device, which is sort of like a motor. If you turn it on, it will start and it will rotate, and it converts the rotary motion into a linear motion, which is what happens in most circumstances if you're moving something from point A to point B. So in this case, I've got about a 15-inch span here, and I'm going to simulate what would happen if we just turn on this motor. And you see, that's really not very good motion control. It moved imagine if this were on a medical device, if it was an MRI machine and you had the patient laying on the tip of this thing here, it wouldn't really be a very good idea to just do that to them. So that's the where of motion control, though. You're moving something from A to B. And I'm going to erase some of this stuff for the moment. If we draw a chart of that, I'm going to draw it a little bit higher so I have some more room. So we've got time on this axis and position here. Basically what we did there was just went from, let's say, position 0 to position 15. And it was pretty much just zoom right up there like that. And so the next thing we said, that's really not a very good idea. That's not very nice to do to our patients, or we're not going to stay in business very long if we do that. So the really hard part of motion control is the how. How do we do this in a safe and acceptable way? And we've come up with the mathematics to do these kind of things through control loops, through hardware that very carefully outputs the current. So I'm going to draw a couple more charts here. This one is velocity, and this one's going to be, I apologize, I'm running out of the room here, acceleration. And I'm glad we have a student in the room, because when I was in high school, a lot of kids were just like, you're never going to use calculus, you're never going to use algebra. This is ridiculous. Where would you ever use this in your life? Well, anybody that stepped on an elevator, someone was thinking very carefully about that, how this thing accelerates and goes, especially modern elevators. You can sometimes barely even feel, the transitions from low to high speeds. So we figured out that a better way to do this, instead of just a straight line, is more of what they call an S-curve, which it really starts at the acceleration phase, where you accelerate up to a certain acceleration, then it decelerates, so it's moving at a constant velocity, and then when you stop, it does it accelerates in the negative direction because you're stopping, which is negative acceleration. So it's a very interesting trapezoidal type of a chart. And what that does to velocity is your velocity is not just a straight, hard, chunky movement. It's more of a nice curve like that, where it slowly goes up to velocity. Then if you imagine the elevator, you're riding up at a constant fast speed, and then it slowly goes back down again to 0 as you reach your floor. And that makes this curve look, much more smooth as you get up to the position that you desire. So I mean, people build their whole careers out of just figuring out how to do this right, because there's all kinds of trade-offs. You can slam somebody into the MRI machine, and you can go through a lot of patients that way because you're not wasting all this time slowly moving in and out. But there's always trade-offs of how fast can we do it, and that's a very personal type of an example, or you can really feel that. But in like a bottling machine, you can't just be slamming bottles in and out, or they'll be breaking and flying all over. But you want to do it as fast as you can. So there's always a trade-off between how stiff can I make this versus how smooth and how fast can I accept the machine to be. So a more typical example would be like slowly start it and then slowly stop it is what we do in motion control. So with that, next time you step on an elevator or on the people mover at the airport, think about vendors have spent a lot of time thinking this thing out and building the hardware and software, and engineers that use that vendor's equipment have thought a lot about exactly how can we manage this trade-off of speed versus comfort, or speed versus quality in machines. So thank you.